So you say the number of products and number of reactants. What does that mean?
Like of each reactant, like I'm not sure.
No, you're close. I mean, you're really close. There's definitely something. You have to have the same number of something on one side as the other. But actually, the number, you can have one reactant and two or three products. So that doesn't always add up. But there is something about a chemical reaction that always adds up. Anyone remember what that is? Yeah, see, I'm getting a lot of answers like both sides are equal, but what does that mean? Equal in terms of what? It's not total charges, because sometimes a lot of chemical reactions, there's no charge involved. You have neutral reactants on one side, you have neutral products on the other. There's no actual charges being produced. So something is the same on one side of the reaction as the other. Actually, there's a couple of things.
Is it the numbers of atoms and elements?
Yes, exactly. There you go. The total number of atoms is the same on one side and the other. So if there's two copper atoms on one side, but they're in a certain compound, when they go through a reaction, there's also going to be two copper atoms on the product side, maybe associated with something else. So the atoms have to balance on each side. You have the same kinds of atoms and the same number of atoms on each side of the reaction. So what does that mean? What else? So what else would be balanced? If that's true, that you have the same atoms on one side as on the other, what else must be true for one side and the other? If I have exactly the same atoms on one side of exactly the same number of atoms of products and at the same number of atoms as reactants, what does that mean for, what else is the same for products and reactants?
The type of atoms.
The type, yeah. So you have the same atoms on each side, and you have the same number of atoms on each side. So basically, you have the same. Each side of the reaction has the same atoms and the same numbers. So what else must be the same? Something we can measure. Sort of took advantage of this in a previous lab. We measured something.
Is it the mass?
There you go. Exactly. It's the mass. So remember when we, in our experiment just last week, we were dehydrating a hydrate salt. We had to make the assumption that when we drove all the water away, that the mass of the hydrate before the reaction and the mass of the anhydrous salt plus the mass of the water that we lost had to be the same. So if you have the same atoms and the same numbers on both sides of the reaction, then exactly right, the masses have to be the same. So that's what the balanced chemical equation means. You have to figure out what the chemical formula is for our reactants and our products, and then balance them to make sure you have the same number of atoms on each side. So use observations from the lab and the different types of reactions. We'll talk about all the different types, and to write the balanced chemical equations. And if you have any questions like during the lab or after the lab, just let me know, because sometimes balancing these reactions can be kind of tricky. So these are some of the evidence of reactions you're going to see tonight. So sometimes you have you have a liquid, you have another liquid, you put them together. It's hard to know sometimes whether or not a chemical reaction has taken place. These are some of the things to look for. So one thing is, let me get my pen out here. One thing to look for is that a solid forms. And you can see, and it's not always something that's like, a big solid that crashes down to the bottom. Sometimes you will see a solution get milky, or you'll see a suspension of like, really small particles. That's also a solid, just really, really small particles. And we call that a precipitate. And when we write a chemical reaction, a lot of times we'll either put S as a subscript after. What does this stand for? If I put S as a subscript after a chemical formula, what does that mean? Yes, do the pre-lab quiz now if you haven't done it already. So what does the subscript S stand for? If I write silver chloride and then put an S next to it, what does that mean?
A solid.
Right, it means a solid. If I have H2O with an L, can't really tell it's an L, it means liquid, and of course G means gas. So another thing that chemists will do to when they're writing out a chemical reaction, a formula, balanced reaction, is they put an arrow, sometimes pointing down, if it's a solid, which indicates it's a precipitate that's falling out of solution. And other times, if they form something like, let's say if they form hydrogen gas, they'll put an arrow going up, meaning that because it's lighter than air, it comes out of the solution and up into the atmosphere. So that's the second one, is if a gas is released. So if something falls out of solution, we know that something new has been formed that is no longer soluble in that solution. So two things that were soluble came together and formed an insoluble precipitate. Or two things came together and formed a gas. So you would have H2 or O2 or CO2 or something. Those are going to be like the three gases we're looking for tonight. So like I said, you would just put comma G or arrow. So pH change, what does that mean, a pH change? How can you tell if the pH has changed?
Color.
Color. But what would you need? That's true, but what would you need to see a color change if the pH changed?
The paper. That paper that you put in?
Yeah, and it's called an indicator. Yeah. A pH indicator. And so the most common pH indicator we use when something is acidic and the pH goes down, it turns pink. And if the pH goes up because it's basic, it turns blue. So that would be a pH change. Either you're producing or removing an acid or a base. So changing the pH in either one of those things. You also can be changing the temperature. So if the temperature goes up while we're doing a reaction, what kind of reaction is that? Anyone remember what that's called? What kind of, we have a name for that.
Combustion.
That's one kind of, that's the type of reaction that releases heat. There's lots of other reactions that release heat as well. There's sort of like, there's a general name for it. It has, oops.
Is it exothermic?
There you go. Exothermic. Yeah, so if a reaction is exothermic, it means it releases heat and the temperature surrounding the reaction will go up. Now, if the reaction feels cool to the touch, that means it's taking heat from the outside and taking it into the reaction. So it's actually removing heat from the surroundings. And it feels cold because it's basically, if you put your hand on something that's absorbing heat, it's absorbing heat from you, and so it feels cold. And the temperature in the surroundings will go down. What do we call that kind of reaction? It's similar to this.
Window?
Endothermic, right. Endo. Exo mean going out, endo mean going in. So like for instance, if you sprain your ankle and you have one of those cold packs, there's a salt in there and liquid on, there's salt and there's a liquid and they're separated. And then when you break the separation, the salt dissolves in the water and it's an endothermic reaction. And so it sucks in heat from around it and makes your ankle feel cool. So another one is look for a color change. Now this doesn't mean that you had to add something beforehand. You could just have a color change. Like a lot of metals, when they form precipitate, have these like really bright colors, like lead, for instance. Lead iodide is it's this beautiful yellow color. And in fact, a lot of the paints, that's why lead was found in paint for so long, because lead turns all these really beautiful shades depending on what you react it with. And so, yeah, it makes really pretty paint colors. It's also super toxic. So changing of color is another one to look for. And then one that we won't be dealing with tonight, but you can see a lot, is just the production of light. Basically, it means that electrons are being excited during some sort of reaction. And we know that when electrons are excited and then fall back, they release light at different wavelengths. And so if you put two things together and light is released, that's also evidence of a chemical reaction. Okay. So here's one of the tests we're going to be doing tonight. Hopefully people have found their wooden splints. If not, I only had one, so I found some matches I'll also be using. So basically we can look for 3 different gases using this very simple apparatus. One, you sort of take, ignite it and then blow it out, and while it's still glowing, put it into the tube. If oxygen is there, it will reignite. It'll just be, instead of just glowing, it'll catch back on fire, indicating that oxygen is there, and a combustion reaction can keep going. Another gas we can look for is hydrogen. One of the reactions we're going to be doing tonight releases hydrogen, and this is kind of fun. So if you have a tube full of hydrogen and you have a match or the flaming wooden splint, and you hold the tube upside down, because hydrogen is really light, it will float away. So you have it upside down, you put the flint up next to it, and it'll go pop. And if that's the case, hydrogen's there. And so this is the combustion. This is the balanced equation for the combustion of hydrogen. 2 moles of hydrogen, 1 mole of oxygen gives you 2 moles of water. And then finally, another reaction we're going to do is going to produce carbon dioxide. Now we know that carbon dioxide is used to put out fires, right? A lot of, some of you may have carbon dioxide flame extinguishers, fire extinguishers in your house right now. So if you have a tube full of carbon dioxide, you take the flaming splint, you put it up there, and instead of going pop, it just immediately goes out. And that indicates that you've got carbon dioxide present. So we're basically going to be testing for all three of those tonight. So here's one of the reactions we're going to be doing, and if you're looking for balanced equation, here you go. So the lime water, probably something you're not familiar with. I haven't seen lime water in forever. Lime water has something called calcium hydroxide in it. And when you see hydroxide, what does that mean to people? What kind of chemical is that? If you have a hydroxide, like calcium hydroxide, sodium hydroxide, potassium hydroxide, if that's dissolved in water, what kind of solution do you have? Give you a hint, do you have an acidic or basic solution? Hydroxide. Does that make you think acid or base? Base, that's right, Ezekiel. Base, and it's a strong base. So be very careful when handling the lime water. So wear the gloves that come in the kit, because bases are actually more dangerous than acids for like spilling on your skin. Acids basically you can wash off and not have much of a problem. Bases actually dissolve organic material, like skin, for instance. So you definitely don't want to spill this on yourself. So anyone tell me what kind of reaction this is? So what is formed here? How do we know that a reaction is taking place? So we're testing for carbon dioxide. Here's what's going to be in the solution. We're adding carbon dioxide. What tells us that a reaction's taken place?
In the equation?
No, just looking at these tubes. So here's our lime water over here on the left, and then we add CO2, and here's what the reaction looks like. What tells us there's been a reaction?
Color change, right? Is one of them. And
Not quite a yes and no. I mean,
but, like, you can.
yes, you could say that there's a color change. There's something else.
It's.
So I couldn't quite hear that. What was that?
Yeah, I was just thinking of another thing to say.
Oh, I thought I heard someone else like way in the background there. So yes, it's a color change, but there's something even more obvious that's taken place you should look for. What has been produced?
It looks like it's foggy.
Mm-hmm. And so that's it. That's evidence of what's being produced.
Like water.
Precipitate. There you go. Exactly. Yeah, like I said, not every precipitation reaction you automatically get like a big lump of something that falls to the bottom of the test tube. I mean, sometimes you do. Sometimes you get something that's like so insanely insoluble, and it forms like, great big particles. But a lot of times you get something like this. You get a suspension, so you get this milky suspension of very tiny particles, but it's still a precipitate. It's still a solid. If you left that for like a really long time, if you left it overnight, came back the next morning, all those small white crystals would be on the bottom of the tube, and the rest of it would be clear. It just would take a long time for that to take place. Right, so that is a precipitation reaction. So really got to pay attention to our safety tonight, people, because we're going to be like handling caustic chemicals, both acids and bases. We're playing with fire, so all sorts of things. So definitely be wearing goggles and closed-toed shoes. If you have like long sleeves on, you might want to just pull them up so they don't get caught on anything. If you have long hair, like I certainly have to worry about that, tie it back. We're definitely going to be wearing our gloves. One of the things we're going to be using is magnesium metal. We have this like ribbon of magnesium metal that we're going to be doing a reaction with. Do not let that catch on fire. Magnesium, I don't know if you've ever seen magnesium burn, but it burns with an incredibly high heat and releases an insane amount of light. And basically you cannot put it out. So don't let that happen. So yeah, keep it away from heat and fire. So like I said, all lime water, hydrochloric acid, peroxide, you're already aware of. Don't let them get on your skin for a long period. Keep in the lab kit for later use. Like if you want to do some cooking, you're probably going to want to use different vinegar than the stuff we've got in here. I'm not even sure it's fit for human consumption. So I probably wouldn't do that if I were you. And then make sure you clean up everything afterwards. So let's just take a quick look at the actual lab itself. And if you have any questions before we get going, you can definitely do that. So where is our, oh, here we go. Oops. Oh, here we go. Okay, so we've got, so here's our first one right here. All right, so the very first activity is a synthesis reaction. What's a synthesis reaction? Someone tell me what the synthesis reaction is. If you had to guess what a synthesis, I mean, it's right there in the title, a synthesis reaction. What do you think that means?
When two reactants or more like combine.
Yeah, exactly. You take two things, they come together, make a third thing. So that's a synthesis reaction. Basically, you have two or more reactants, but you only have one product. So those two things or three things that are reactants come together and form a new compound. So basically what we're going to be doing here is taking some steel wool and reacting it with air. So what do you think our product is going to be if we take steel wool and air and put them together? What do you think is the reaction that takes place? What happens to metal in air?
It corrodes.
Yeah, it corrodes, right? It rusts. What is that? When if you see like an old car with like a big rusty bumper on it, back when they used to have bumpers. What is that? What reaction is that? Do you know? Basically anything you leave outside, any kind of metal you leave outside will corrode or rust over time. What's actually taking place? It's a synthesis reaction. What do you think the metal is reacting with?
Just oxygen, the air.
There you go. Yeah, Ezekiel. Yeah, and oxygen. Right. Oxygen. You're forming oxides. So it's actually, so the reaction here, what we're doing, we're taking iron, the main part of steel. We're taking iron, and we are reacting it with oxygen and forming iron oxide. And basically what we're going to see is we're going to try and tell whether or not that's an exothermic reaction or an endothermic reaction. So we're going to dip it in some vinegar that helps like strip some of the coating off of the steel wool and leaves it available for the oxygen to attack. Now, if it's an exothermic reaction, what's going to happen to the temperature? We're going to put a thermometer in there. What's going to happen to the temperature if it's an exothermic reaction?
It's going to increase.
Right. Temperature is going to go up because that reaction is going to release heat. But if it's an endothermic reaction, it's going to suck up heat from the surroundings, and the temperature of the thermometer is going to go down. So we'll see what happens with that one. So the second one, we're going to do a decomposition reaction. Now, what's a decomposition reaction? When something decomposes, what does that mean?
It breaks it down.
Yeah, it breaks it down. Basically, it's the opposite of a synthesis reaction. A decomposition reaction takes a single reactant and breaks it down into two or more different products. So what we're going to be doing here is looking at the decomposition of hydrogen peroxide. So, and then we're going to basically see what the products are. We're going to test to see what the products are. So because we have hydrogen and peroxide, what do you think are two basic, what do you think our products could be? We've got hydrogen, we got oxygen. What do you think our products could be?
I accidentally got it off. No, it says connect airline tubing to the top, the larger end of the pipe.
So we've got hydrogen and we've got oxygen. What do you think our two products could be? Actually, three different types of products could be. So I've got H2O2. That's going to break down. What are my potential products, do you think?
H and O.
H and O. Now, are those going to be, is that how we find hydrogen and oxygen in nature? That's just H and O?
Or like H2 and O2.
There you go. Yeah, that's how we're either going to make hydrogen or we're going to make oxygen, or we could make both, I suppose. And what's another potential product? I could have hydrogen, I could have oxygen. What if they're combined? What do they typically make when you combine them? Like, what's the most common product when I put hydrogen and oxygen together?
Water.
Water, exactly. So we're going to look and see which gas we're going to make. We're going to make hydrogen, we're going to make oxygen, maybe we're just going to make some water as well. So if I put a glowing splint, so you can see here, we're going to test that by putting a glowing splint into the test tube that we're gonna collect some gas. Now, if it's hydrogen, what's going to happen? So remember, a glowing splint would be, it was burning, but then we blew it out, and we put it in the presence of hydrogen. What's going to happen? What do we think? Is it going to go pop? You're free to take a guess.
Yes.
Well, probably not. Probably not. Because hydrogen wants to burn. And if there's no oxygen present, and it's just glowing, it's not actually on fire, probably nothing will happen. Although there is a chance it might go pop. However, if you put a flaming splint in there and it's hydrogen, it will definitely go pop. What if it's oxygen and you put your glowing splint in there? What's going to happen?
Is the fire gonna get bigger?
Yeah, it'll actually catch fire. So basically, you're putting it into an oxygen-rich environment, and that basically speeds that reaction up, because you've got the wood in the splint, which is one part of your reaction, and then you're increasing the concentration of oxygen. So basically, you're speeding the reaction back up, and it should burst back into flame. But if you put a flaming splint, it's already on fire, and you put it in the presence of oxygen, what's going to happen? What do we think? Is it going to go pop? That's our main thing, because it will pop if it's hydrogen. Is it going to pop if it's oxygen?
No.
No, that's right, it won't, because you're not burning oxygen, right? You can't burn oxygen. Oxygen's the thing doing the burning. So it might glow a little brighter, or the fire might get a little larger, but it's not going to go pop. Hydrogen will. So that's basically how we're going to tell the difference between if we're burning hydrogen, or if there's oxygen present. So the next one, what's a single replacement reaction? Who's read this stuff? What's a single replacement reaction? Has anyone read this? It's sort of like a waltz. Oh, there you go. Yeah, Ezekiel's on top of it. It's sort of like a waltz, like you've seen in old movies or even new movies, where you'll change partners. So basically, it means that an atom is bound to one other atom, one partner, and then during the reaction, basically is swapped for another one. So in this reaction, this is where we use the magnesium. So you want to be careful with it. And we're going to take the magnesium and put it in the presence of hydrochloric acid or HCl. So what takes place in that reaction is that the hydrogen that's bound to the chlorine changes partners. The chlorine changes partners with hydrogen and then reacts with the magnesium. So we form magnesium chloride rather than hydrogen chloride, and then the hydrogen is released as a product. So here we're actually going to be making hydrogen in the tube. So this is going to, this might get a little bit messy. so make sure you have a place you can keep clean, because we're going to be doing this reaction underwater. Because when you're dealing with hydrogen, you want to see the bubbles form. And when the bubbles are forming, basically they'll be pushing out. You'll have a tube full of water, and the hydrogen will be forming in the tube and pushing, forming bubbles and pushing the water out. And once the hydrogen has pushed all the water out, then basically we know we've collected enough hydrogen. And then we put our finger over it and then do a test. Okay, so that's the third one. So we'll be using hydrochloric, fairly concentrated hydrochloric acid for that one. So you definitely want to be wearing gloves for that too. So double displacement reaction, same as a single displacement reaction, although in this case you've got two atoms bonded to two other partners, and basically they both swap. And so in this one, we're using baking soda and vinegar. So we've got baking soda, sodium bicarbonate here, and vinegar is acetic acid. And basically we're going to be swapping them. So we're going to be forming sodium acetate, and the vinegar, which is hydrogen, and along with the acetate. And the hydrogen is going to go to the sodium bicarbonate. Then the sodium bicarbonate actually decomposes and forms CO2. So we can go through, as we're doing the reaction, so we can also look at the chemistry and how this occurs. Basically what we're looking for is you take vinegar, you take baking soda. I think everyone's probably seen that demonstration in middle school or in high school. It releases a lot of CO2, right? You get that volcano. But what happens? That happens because of a double displacement reaction. So we're basically going to be doing the same sort of thing. Number 5 is classic combustion reaction. And we're going to be looking to see what the products of the combustion reaction are. And so we're going to be burning a candle. A candle is a hydrocarbon. Basically, a hydrocarbon is what it says. It contains hydrogen and it contains carbon. Those are the two things, the two elements in a candle. So when we burn it, when we combust it, what are the products that form when you burn something with hydrogen and carbon in it? So basically I take hydrogen and carbon and I add oxygen. What are my products going to be? Basically going to get two products. Each one of them is going to react with the oxygen. So what do you make when you burn something? Typically, like when you burn gasoline in a car engine, that's also a hydrocarbon. What are the products that come out of the tailpipe?
CO2.
That's one of them. Yep, CO2. Greenhouse gas. So we form CO2. That's one of them. So the carbon in the hydrocarbon gets oxidized by oxygen and forms CO2 gas. What about what happens to the hydrogen of the hydrocarbon? What does that form when you react it with water? And if you've ever seen like a tailpipe in a car on a really cold day, you can see the other product. Because sometimes you will see something drip out of a tailpipe on a cold day. What's that? Hydrogen, oxygen. What's our other product?
H2O?
Water. Yeah, exactly. Water is our other product. So that's what I was saying, that on a cold day, you don't see this in the summer. Well, like there's ever summer around here, but you know, when it's really, really cold, you produce H2O gas, of course, in your engine. But by the time it gets to the tailpipe, it's so cold that it turns back into a liquid. And so you probably have seen water dripping off the end of a tailpipe when it's really cold. So the CO2 remains a gas and goes up in the atmosphere. But the H2O turns back into a liquid, and you can see it coming out of the tailpipe. So basically, we're going to be just basically burning the candle, collecting some of the gases, and seeing if we can look for the presence of water and CO2. The sixth reaction is a precipitation reaction. So this is the one where we're going to be using the lime water. Why isn't, there we go. What the hell is going on? Here we go. So we're going to be basically making CO2 and then bubbling it into lime water. And so what's CO2, when we mix CO2 with the calcium hydroxide. So here's the calcium hydroxide here. When we produce CO2, we then get a swap out. We get a single replacement reaction where the calcium hydroxide then forms a calcium carbonate. And that is a precipitate. And that will basically, that's where you will see the clear solution of calcium hydroxide get all milky and cloudy because it'll be forming a precipitate. So that will be a little bit tricky to do. We'll go over how to do that one. And then the last one is pretty straightforward. Yeah, I know it's going to be a long night. So the last one is, oh, that is the last one. 6 of them. Thought it was, oh no, 7. Yeah, 7 is the combustion, and we're actually, this part will be fun. Very, very short. Has anyone ever burned steel wool before? Because you'd be surprised, because the first reaction, we're actually oxidizing steel wool, right? But in the last one, we're oxidizing steel wool again, but this time we're doing it rapidly. So basically, you'll be, I don't know, maybe you haven't seen this before, but if you take steel wool and set it on fire, it'll burn. So yeah, metal can burn pretty rapidly too. So that one's a little bit dangerous. So make sure that things don't get out of hand. but that's a very rapid combustion. So metal can combust too. Like I said, magnesium as well. And so we don't want the magnesium to burn. The steel, the iron won't burn quite as rapidly or as hot as the magnesium does. So why don't we get set up? I'm gonna, first of all, there's gonna be a ton of questions, I'm sure. Any questions before we get started? Just gonna just sort of knock these out one at a time. Does everybody have all this stuff together? I know there's a lot of stuff to get together. I'm still not sure I have all the stuff, but I think I get everything together. Does everybody have everything that they need? Hopefully you've gone through and looked. There's a long list of stuff to get. Hopefully you all have it. So what I suggest is we take like about 10 minutes to get everything ready in one place, goggles on, gloves on, and then we'll get started, okay? Okay, I see some thumbs, good. All right, so I'm just gonna pause for about 10 minutes, get everything together, and then we'll start with experiment number 1. All right. All right, hopefully everyone's got all their stuff together. So if you could have your cameras on, might be helpful. So you just, check in, see how everyone's doing. So this one's fairly straightforward, as I mentioned. So first we're going to do activity 1, synthesis reaction. So we're taking our steel wool here, and you can just pull it apart. You want about half. If you can't pull it apart, you can just take a pair of scissors. In fact, I might do that. There we go. We'll sort of make a little space to put our thermometer. Not seeing too many cameras on, people. So you want a 50 ml cylinder, okay? And it says 50 mils of vinegar. So here's our vinegar here. And everyone knows that vinegar kind of smells kind of funky. So you want 50 mils. And you don't have to be super precise on this one. That's about 50. I got myself a little Pyrex. You can basically anything that holds liquid is fine. And so check the temperature of the room. So remember, you don't want to grab the bottom, obviously, because you'll increase the temperature. And remember, when you read temperature, you read it to the first 2 digits. You should be able to read fairly well, like 15 degrees, 16, 17, 18, whatever it is. And then you have to estimate that last digit. So if it's right on the mark, you say 15 or 16.0. If it's halfway, 0.5. If it's a quarter of the way, 0.2, 0.3. But you always estimate the last digit. So you should have 3 significant digits in your temperature, okay? I'm looking at mine, and I get little bit more than 15, so I'm going to say 15.1. So I'm going to write down, so you write down your room temperature. The initial temperature is 15.1 degrees, okay? And then we're going to soak. Soak it in the vinegar. Still not seeing any cameras, people. Is everyone doing this tonight, or you're planning on doing this later? Hey, Rachel. So you're doing it tonight, right? You're a chemistry warrior. I knew it. And you'll see that the steel wool absorbs a lot of liquid, like almost all of it, not quite. And just keep it in there for about 2 minutes or so. Yeah, it's going to smell a little gnarly, but you know, any good chemistry has to smell a little bit gnarly.
Is this how we're supposed to pull it apart? Like that?
Oh, you can? Yeah, that's fine. Yeah, and then just basically you want to wrap it around the thermometer. So what's happening here is that you may notice that cars that live by the ocean and cars that sort of spend their life in the desert, you ever notice that, like, you go to Arizona or something and you see cars that are like, 40, like old VW bugs or something with not a spot of rust on them. Why is that? I mean, it's not like they lack oxygen in Arizona, although it definitely feels that way sometimes. Why is it that cars rust a lot faster on the coast than they do in the desert? Anyone take a guess of why that would be the case?
Humidity?
Yeah, exactly. So what about the humidity?
The amount of water that's in the air.
Mm-hmm. So why is it that water helps oxidize the metal? Because the water's not actually involved in the reaction. It's metal plus oxygen makes rust. Not the water really isn't involved, but it's important. So what does the water do, you think?
The lesser the water in the air, the least likely the car's gonna rust.
Someone's singing beautifully.
Or your grandma's mass in the background.
Oh, cool. So what the water does is actually the water has dissolved oxygen in it. And it allows the oxygen to have very close and sustained contact with the metal. And so if you have a lot of water on the metal all the time, you have very close and sustained contact of oxygen dissolved in that water with the metal. And so the oxygen doesn't escape, it stays there. And so it allows the reaction to take place. So the water doesn't actually do anything. It doesn't participate in the reaction. Basically, we would say it is a catalyst of the reaction. All right. So I'm going to squeeze out my extra and put my thermometer in here. And basically take one of the rubber bands and just sort of tie it. And then just keep your eye on it. Give it about 10 minutes Although I can already see something's happening. That's kind of cool. So come on, Rachel and I are the only ones doing this experiment. Come on, somebody else has got to be doing this right now. Nobody else? Man, it's going to be a long night of watching me do chemistry if that's the case. Come on, I want to see if people are doing the experiment. Is anyone else doing the experiment? Brandon, yes, you're doing it, right, man? You got goggles on. You don't actually watch. You don't put your goggles on to watch chemistry videos. I hope, or maybe you do. Maybe maybe that's the way you do things. Cool. You should see something happening. Any guesses as to what happens to the temperature? Since this is an oxidation reaction, what do you think? And we know that combustion is an oxidation reaction. What do we think is going to happen to the temperature? Is that going to be an exothermic or an endothermic reaction? What do we do with the steel wool? Oh, pull it. You can take a pair of scissors and cut it in half, or you can just pull it apart. So we need half the steel wool for this experiment, and then we're going to use the rest at the end. In fact, we're going to do one other thing with it too, involving the magnesium. I'll let you know when we get to it. So is this an endothermic or an exothermic reaction? What do people think?
Exothermic.
Yeah. Basically, most oxidation reactions are going to be exothermic because, I mean, what we're doing it very slowly, but we are burning the steel wool, actually, slowly, but we are still burning it, because burning just means combining with oxygen, generally very rapidly. But now we're just doing a slow burn. And that is an exothermic reaction. So in fact, yeah, my temperature's gone up from 15 to about 21 degrees in just like a few minutes. So you can take like a temperature after, 2 minutes, after 5, after 10 minutes. And then, so in the handouts, and so I want you to, when you send in your report, use one of either the Word template or the PDF template. And so there's questions associated with each experiment. And so you have to answer all the questions. And then the last one, I think pretty much the last question on all of them is balance the chemical reaction. So what do you think is our chemical reaction here? First of all, what are our reactants? We have basically two reactants here. What two things are participating in the reaction?
The wool and the vinegar.
Nope. Now, if you've read it says right here, vinegar does not participate in the reaction. So like I said, cars rust faster next to the ocean than they do next to in the desert, because the water allows the oxygen to get close to the metal. So vinegar is not actually involved in the reaction. And it's not the wool. What's the actual, because wool's that's not a chemical. What are the two things that are actually involved in the reaction.
Is it iron?
Iron's one. Yep. So iron in the steel, because iron is, 95% of steel, depending on what kind of steel it is. So iron is one thing. And what's the other one?
Oxygen?
Bingo. Iron and oxygen. And so iron, how are we going to write iron in our reaction? What's the chemical symbol for iron?
Fe.
Fe. So is it just Fe by itself, or is it like Fe2, Fe3? What do we put down for iron? Does it exist by itself as a metal? Do we just say Fe, or is it a molecule?
It's a molecule, I think.
Well, it's a big molecule, but we just say it's just Fe, because it's basically iron is just a whole series of atoms of Fe all just sort of living together in peace and harmony. So we just say Fe, because they're not isolated into molecules. So it would be Fe plus oxygen. And what do we put down for oxygen? What's the chemical symbol for oxygen? Oxygen. What's our chemical symbol for oxygen?
Oh.
But that's the chemical symbol for oxygen. What is the chemical symbol for oxygen gas?
O2.
O2, right. So we have Fe plus O2 makes iron oxide. Now, this part's a little bit tricky. What is a formula for iron 2 oxide? Now, when I have 2, what does that mean? If I have iron and then in brackets 2 oxide. What does the 2 stand for in iron 2 oxide?
It's a charge.
Right.
Plus
Right,
charge.
it's an ionic compound, iron oxide. So does iron form a positive charge or a negative charge?
Positive.
Yeah, it's a metal. Metals form positive charges. Oxygen is a non-metal, it forms a negative charge. So what would be the formula for iron 2 oxide? So the 2 means iron has a 2+ charge. What charge does oxygen have when it's an ion?
-2.
Right. So if iron is +2 and oxygen's -2, what would be the formula for iron 2 oxide?
FeO.
Excellent. All right. So I think I'm going to call mine. We'll look at the final temperature here. Looks to be about 23.5 degrees. So my temperature's gone from 15.1 to 23.5. So definitely signs of an exothermic reaction. So let me get some of this stuff out of the way. So with the second one, I definitely need some cameras on, people, or I'm just going to shut down.
Where are we writing the temperatures for like our room temperature and stuff?
You should be writing them, just like have them in, write them down like in notes or something, and then you want to put that in your report.
Okay.
So yeah, so just should have a notepad or hopefully even better, a lab book.
So what do we put in data table 1 then? Is that just like the notes?
Yeah, data table 1 has. Yeah, it's hard to use this thing with gloves on. Here we go. Yeah, so data table 1, basically just, yeah, so the observations would be basically, what did you see? What did you measure? So did you see a color change? Did you see a precipitate form? Did you see light given off? Did you see a temperature change? If you did see a temperature change, what was it? What was the temperature at the beginning? What was it at the end? Okay. And then the questions are after that. So activity 1, describe all the signs that indicated a chemical reaction occurred. Describe the temperature change. Was heat released or absorbed? And then describe any other changes that you might see, and then write a balanced reaction. And so it also says, make sure you include the heat energy in that reaction. So for an exothermic reaction, where heat is produced because of the reaction, would we put heat as a reactant or a product? Product, exactly. So it would be Fe plus O2 gives you iron oxide plus heat. And then later on, when we do some more of these types of reactions, we'll actually, not only will we be balancing the atoms on both sides and the mass on both sides, but we also be balancing the heat on both sides as well. So that's called thermochemistry. I'm sure you're all excited to be getting into that. Okay. So number 2, but the hydrogen peroxide. So now we've got our 10 mil graduated cylinder. And here's our hydrogen peroxide. I believe it's 3%. You typically can only buy like 3 or 5% hydrogen peroxide. If you're in a chemistry lab, you can get like 50% hydrogen peroxide, but it's super reactive. And so you don't want to really have that around. So 10 mils. So remember, when you're measuring, you want to get down to the level where it says 10 mils when you're pouring it in. Yeah. Okay. Then you have a large glass test tube. I had a large, I got all my stuff together. I have my large glass test tube. Yeah. So yeah, so you want, so there's a number of test tubes for this experiment. There's a little glass test tube that we'll be using later, the big one here, and then there's plastic ones as well. But for this, you're going to want to use the large glass test tube. And then this is our 250 ml beaker. Put that in there. All right. Got that in there. So plastic mini spoon. This bad boy right here. Very, very small. And we have a packet of dried yeast. Should have this packet of dried yeast. Now, let's test and see who's actually read this thing. What in the yeast actually causes this decomposition reaction to take place? I want two spoonfuls, right? 2 level spoonfuls. One. Two. There we go. Sort of mix it up. Let the reaction. You can. So, is that evidence that there's a reaction taking place? Anyone see what's happening there? So where's the evidence of a reaction taking place? It's going to be a long night, people.
Is it the bubbles?
What does that tell us? Yeah, we're definitely seeing bubbles. What does that say?
There's hydrogen.
Nope. Because every time you see bubbles, does it mean you're producing hydrogen?
No.
What does it mean? I mean, you could be producing hydrogen, but the bubbles means what?
Precipitate? No.
So when you form a precipitate, do you see bubbles forming? What normally means you got bubbles? Like if you're in the tub and you got bubbles, what's filling the bubbles?
Outside?
What's inside those bubbles?
Gas.
Gas. Right. So yeah, air. So in the tub, you got bubble bath going. You got air inside the bubbles. Here, we're making a gas. We just don't know what it is. So we're going to check and see. So now we'll take a glowing splint. So here's our splint. I've only got one. I don't know how many you guys got, but I just got the one. So glowing basically means it's not burning. So you get it burning and then you blow it out. I didn't see anything. Maybe my reaction is over. I think I might have spent too much time gabbing. There you go. Now, do you see what happened? What just happened there? Just happened again
Combustion?
and again. Yeah. So what does that indicate? Even if it doesn't catch, you can see that it glows more brightly when you put it in there. So what does that mean? What gas have we produced? So it was glowing. You can still see it kind of glow. It's kind of cool. But then when I put it in the tube, it burst into flames. What does that mean? Now, if it was CO2, what would happen? If I have fire and I put it in CO2, what happens when I take something that's burning and I introduce CO2? Anybody? I'm not going to look at the chat. I need you to talk to me. If I have something that's burning and I put it in the presence of CO2, what's going to happen?
It's gonna explode.
Why would that happen? What happens when, why is CO2 used as a fire extinguisher? So if I have a fire, I have a CO2 extinguisher, it actually puts the fire out. Because basically what happens with CO2 is it replaces the oxygen in the fire. And oxygen is required for a fire to burn. So if CO2 replaces all the, like basically replaces all the oxygen that's present, the fire goes out. Because the oxygen that's in CO2 is already oxidized. It's already reacted with the carbon. So it can't oxidize anything else. And so the fire goes out. So if I put it, CO2 actually puts the fire out. So if I had something that was glowing, not burning, and I put it in the presence of a gas and it caught fire again, what gas is that? We now know it's not CO2.
Is it O2?
It's O2, right. We couldn't have made CO2 because remember, we're breaking down hydrogen peroxide. So the only two elements there are hydrogen and oxygen. So we're either making hydrogen, oxygen, or water. And so if it's oxygen, it's part of an oxidation reaction. It's part of a combustion reaction. It causes the combustion reaction to speed up. And so it goes from glowing to burning. If it was hydrogen, it might have either popped or done nothing, because hydrogen by itself can't sustain a combustion reaction. It needs oxygen to do that. We can't just burn hydrogen by itself. It won't burn. In the presence of oxygen, it sure will. So that tells us that oxygen was present. That was one of the products of this reaction. All right, so let's move to 3. So 3 is the one where we need the magnesium and the small glass test tube. So it's a bunch of things we need for this one. So I need to get my small glass test tube. So I've got it here. You can see I've got my small glass test tube along with some plastic test tubes as well. I need to find a small stopper. To find it, where did I put it?
There. Professor?
Yes. Oh,
Are we submitting pictures for the lab?
yep. So hopefully you've been taking, for the people actually doing this experiment, hopefully you're taking pictures. Add the stop.
Where are we supposed to find the large test tube?
It should be, it's the big one here. It's in the kit. You don't have one?
I don't think I have one. So can I use like the small one, or will that like?
Well, you're gonna need the small one for this part of the reaction. I guess you could if you clean it out. Man. Where is my, what's the problem with these? It's so many different parts. Where did I put it? I had it this afternoon. And I put it. All right, give me a sec to find this. Oh, here it is. Good. Found it. Right, so you have two stoppers. You have a little one here. Then there's this big one we'll be using, and this big one we'll be using later. So you can see it's a lot smaller. This one's for the big test tube, and this one's for the small one. So finally. So there's a trick to this experiment you should know. So when you take, so your magnesium ribbon comes in a little bag. So you see there's a little strip of magnesium here. You want about 1 centimeter or so. Doesn't have to be super precise. But one thing, I don't know if you can really see, but on the magnesium should be a shiny, silvery metal. And I don't know if you can tell, on here, there's sort of, the surface is fairly shiny, but it's not completely shiny. So there's a thin layer of something on the magnesium. So what do you think that is? And I'm going to be removing it with the steel wool. So basically just sort of like you were sharpening a knife. And you should notice how, see how the magnesium is a lot shinier now? Basically, I'm removing a layer of something off the metal. Now, what do you think that something is? cut about 1 centimeter. So then you just insert it into, so there's a tapered end and a wide end. So you just insert the magnesium into the tapered end. So has anyone come up with what we just removed from the magnesium? Anyone at all? Anyone even remotely paying attention to what's going on? Apparently not. So,
Yes.
all right. So we've got our beaker, for a 250 ml beaker from before. So you fill it almost to the top, not quite to the top, with water. Give yourself a little room, about that much. So fill it to about the 250 mark or so. Now we're going to get our, now this is where it gets a little kinky because we want our HCl. So it comes in an eyedropper, sort of, or it looks like an eyedropper. Obviously, we don't want to use that as an eyedropper. So 1 molar hydrochloric acid. Anyone know what 1 molar means? It's a measure of something. And you guys are just super active tonight. You want about 3 mils. So we got a 10 mil graduated cylinder, put about 3 mils in there. All right. Now, be careful handling this because, like I said, this is acid. It will burn you. We take our cylinder, our test tube, and we add our 3 mils of acid. So I'm just going to put plain water in here. This part's a little tricky to do. So get one of the transfer pipettes, which, remember, those are the ones with the plastic with the bulb. Should be a ton of them here. Here we go. So transfer pipette. And you're going to add the water. Now what you want to do, this is a little tricky, you're going to want to add the water to this, but you don't want to mix it, which sounds kind of strange. So what you do is you sort of turn it at an angle like this, and you sort of slowly add the water. You try not to mix it too much, so you just add it gently. Just let it run sort of slowly down. And then you just about fill it to the top. Not quite to the top. Leave a little bit of room. You can see that. Then we take our, and we try to put it in there without leaving a bubble. That part's gonna be a little, maybe it should add a little bit more water. Make it a little easier for myself. There we go. And you can do this over the beaker. There we go. Now, some water is going to pop out the top. Now, put your finger over the hole, turn it upside down, and do not let go of it until you get it under the water. Then you can let go of it. And do you see what's happening? What do you see taking place there? What's happening inside the tube? Is anybody even awake at this point?
Is that fire? I mean, is it lit up?
Is it fire?
Sorry,
Oh,
maybe it's just the lighting.
oh, just
Oh, the bubbles?
yeah, bubbles. So there's a gas being produced by this reaction. And if you see the top of the test tube, I'm not going to take it out of the water, but notice that this used to be completely filled with water, and now notice how it's being pushed out. If you look at the bottom, there's bubbles sort of coming out of the bottom of the tube. There goes one. And gas is displacing the liquid that was in the tube. So basically, we're just going to let this reaction go until all of the liquid has been displaced by gas. Then we're going to see what the gas is. It's going to be exciting. Is anyone doing this reaction except for me and Rachel? I think Brandon was with us for a while.
I had to redo the second one.
The second one? Okay.
So for the observations, what should we put like after the minute has passed?
For what?
For the decomposition reaction?
Well, what did you see?
I saw like it fogged up and there was like bubbles forming.
There you go.
Okay.
And that's what you saw. Yeah, I mean, so there's supposed to be your observations of your reaction. So yeah. Yeah, this reaction is working a lot better than I thought it would. But yeah, it's really important to clean the magnesium, the ribbon. So has anyone come up with what the coating of the magnesium was? Why it wasn't as shiny as it was after I polished it? sort of goes back to it's the very first experiment we did. What was the first experiment? Yeah, just talking to myself tonight. Okay.
It was a synthesis.
Yes. What was the reaction? We had steel wool.
The temperature rose.
Mm-hmm. What did we make? We had the steel wool and oxygen. We made something. What did we make? What was the product of that reaction? So we had iron, we had oxygen, and we made something. What was the product of that reaction? I mean, you're gonna have to write a balanced reaction for that anyway. So do you remember what it was? What the product was?
Was it FeO?
Mm-hmm. What is that? What do we call that?
Iron oxide.
Exactly. So if iron plus oxygen makes iron oxide, what do you think was the coating on the magnesium ribbon, since it was also exposed to air?
Magnesium oxide.
Bingo! Exactly. So you have a thin coating of magnesium oxide on the ribbon. So actually, that won't react with the hydrochloric acid because oxygen is already reacted with that magnesium. You want fresh magnesium. You want clean magnesium metal reacting with the hydrochloric acid, with the HCl, because chlorine will not be able to dislocate oxygen. Once oxygen's reacted with something, it's done. It ain't going to be reacting with anybody else, pretty much. And so we need clean magnesium metal. And so when I polished it with the steel wool, it basically scraped that layer of magnesium oxide off the metal, made it nice and shiny. And now you can see that basically all of the liquid is gone from this tube. Pretty much all of it is. And so basically the reaction is stopped because all the HCl has been pushed out of the tube by hydrogen gas. And you can still see we still have like magnesium metal left. So now what you want to do is you reach in. Now this part again, you want to be careful because you don't want to release all the hydrogen gas. So you go in there and you pull out, put your finger again under the tube so you don't want to let any of the gas out. And then you hold it, keep it upside down, and pull out the cork. Again, do not tip this up because whatever gas you've got in there is going to escape. So I pull it out. And now, let's see what happens. I'm excited. Did you hear that?
Yeah.
See if it'll do it again. I don't think so. But... Oh, one more. And I think we're done. Yeah, I think we burned it all. Yeah, so that little pop it sounds adorable. That little pop was the combustion was the combustion of hydrogen. So if that had been oxygen in there, I don't know why it would have been oxygen in there, but if it had been oxygen in there, maybe the flame would have burned a little more brightly, but it wouldn't have made any sound. So that pop was actually hydrogen being burned by oxygen, and water is our product. So cool. I'm glad that worked. That one's always a fun experiment to do. Okay. So next one, we want our cup that had the vinegar in it. So that's what I was using here. So we're going to use that one again. Now we're going to add sodium bicarbonate, better known as baking soda, to it. So we wonder what bicarbonate means. Carbonate is CO3. That is a polyatomic anion. And then when we add a hydrogen to that, so that would be HCO3, we call that either hydrogen carbonate or bicarbonate. So basically it's a carbonate that has an extra hydrogen, or actually a single hydrogen. It's only got the one. So we'll need so again, you want to use weigh boats. Put it on our scale, tare the scale, and we want 10 grams. Now it says 10 grams, it doesn't say 10.0 grams, so you don't have to be super duper precise on this one, but around 10 grams. I would definitely use a spoon for this. If you start pouring it out of the container, it's going to make a huge mess. Yeah, but one spoonful appears to be about 10 grams. One heaping helping is about 10. Man, almost exactly. There we go. If you go a little bit over, no biggie, because it said 10, it didn't say 10.00. All right, so just take this, and when you're transferring solids, you notice if you just bend this, you make a nice little funnel. Makes it, so you pour it in there and automatically you can see reaction taking place. I'm going to put so yes, you might want to take a picture right after you add it, because it's pretty obvious there's a reaction going on. All right, so sort of swirl it around, get that reaction going. So we're going to take our flaming splint and put it in there. So that'll get going. Here we go. Burn. There we go. So put it in, and what happened? Can you see that? Make it a little more obvious. So burning. What happened?
The flame went out.
Mm-hmm. So what does that tell us?
There's CO2.
Mm-hmm. Yeah. It extinguished the fire. So if it was oxygen, that would have like burned it a little more rapidly. Now let's try that again. Now I'll put the sort of, instead of it being on flaming, I'll just have it glowing. So get the, and nothing. So it even puts out the glow. So even when it's just glowing, the glow stops. So basically it extinguishes any combustion at all. Even if it's like on a low level, when it's just glowing, shuts that off. And when it's actively burning, shuts that off. So yeah, that tells us, again, that's carbon dioxide. So here's a question for you. How come I don't have to hold this upside down? But the hydrogen, remember, when we had it in the tube, I had to make sure I held that upside down so that the hydrogen wouldn't escape.
Does that have to do with the density?
Yeah, it does. So yeah, I've got CO2 in here, but it's still in there. So what does that tell us about hydrogen and CO2? Tells us something about the density. You're absolutely right. What does it tell us?
CO2 has a higher density than oxygen.
Then hydrogen, right? We're comparing it to hydrogen.
Yeah.
So actually it tells us two things. Not only does it have a higher density than hydrogen, but it must have a fairly similar density to what? If it's not rapidly escaping all over the place, what must it have either a similar density or a higher density than what?
Oxygen?
Or air. Yeah, just the air. So like 78% of the air we're breathing is nitrogen, and then the rest is like oxygen and a bunch of other things. But yeah, but it must be fairly similar density to air or slightly heavier than air for it to stay in the cup and not escape. So basically we've learned two things about the CO2. It puts out, not only will it stop a combustion reaction, it also has a density equal to or greater than air. All right. So combustion reaction. So hopefully we have I have my candle here. Oh, here we go. Put this down. There's my little candle. Get it going. All right. So again, I take my small glass test. That makes a pretty glow in the video, doesn't it? So take the small glass test tube again. You may want to clean it just because there may be just, because I don't know if anybody can see, there's something really important there. Can anyone see what's in the tube? Right about here. It's kind of hard to see. Right. Look where the candle, right above the candle. Anyone see what that is?
Is that like residue?
Yeah, what is it? Little droplets. What do you think the little droplets are? What was the last thing we did with this tube? We combusted something. What did we combust in there? We collected a gas underwater, remember? What was the gas we collected?
Hydrogen.
Uh-huh, and then we combusted it, right? What's the products of, I popped my peas there. What's the product of a hydrogen combustion reaction? Remember, combustion reaction, you're rapidly reacting it with oxygen. So I've got hydrogen, I'm rapidly reacting it with oxygen. What's my product going to be?
Is it H2O?
It certainly is. So that is the product. You actually saw it, the remnants of it on the side of the tube. There's tiny little droplets of water in there because that was the product when we blew up the hydrogen. It makes water and it forms these teeny tiny little droplets in there. So you may want to clean those out. We have like a cloth, a piece of paper towel or something. Clean that out because we want to collect the gases from this reaction. So we're going to hold it over the tube, hold it over the flame and collect gases. So hold it over. You don't want to put it right over it and then put it out, but basically hold it over it and allow the gases from the reaction to collect in here. Don't hold it, obviously don't want to burn your fingers. Yeah, if you get it too close and it goes out, you will get a dark residue on the tube. What would that be? You know, when you're burning a candle and you put it out, you get this black residue left over. Anyone know what that is?
No.
Carbon. Just pure carbon. Has anyone heard of buckyballs? It's a new form of carbon. It was discovered about 15 years ago. Anyway, it's a brand new form of carbon. It was actually discovered in the most boring place. It was discovered by burning a candle. And now all sorts of exciting new things are being produced from it. Like carbon nanotubes and all that kind of fun stuff. So now keep the tube inverted because whatever gas was in there, we want to keep it in there. So I'll put in there and went out. So we can guess at least one of the gases that was produced by the flame, by the candle flame. What was it?
CO2.
Mm-hmm, exactly. CO2 again, our good friend CO2. And now, if you look again, you can see there's even more water than there was before. So that basically tells us that was our other product as well. I mean, obviously you can't prove that that's water. You'd have to test it, but it looks an awful lot like water to me. Very small, clear drops, more than likely water. Okay. Oh, shouldn't hold. There's one more thing to do with the candle. That also goes back to the density question. So I've got I still haven't tossed out my baking soda and vinegar. So I've still got it here. So they say add another 50 mils of vinegar. Measure out 50 mils of vinegar. Then boom, you can see the reaction going on big time. I'm producing lots of gas. And then watch what happens. Oop, oop. Come on. It's not working. Come on.
Doesn't the fire go out?
It should. Yeah, it's just to be able to pour the CO2 right on top of it. Like, but for some reason, I can't do it here. Maybe it's the shape of the cup or something. No. Come on. No, it's not doing it. Yeah, you should be able to just pour the CO2 because it's slightly heavier than air. But for some reason, I couldn't get mine to do that. So see if you have any more luck. Because as we saw, it's slightly heavier or the same density as air because it doesn't escape. We could put our splint in there and it went out. So there's obviously CO2 in here. But yeah, for some reason, I've done that before and it works. So interesting. All right, so So I'm going to have to clean out this test tube. All right, so you just basically go back for the large test tube. You want to wash that out because it had like yeast and a whole bunch of other good stuff in it. So this one, we want now we make a glass collection stopper for this. You take the large stopper and you cut a piece of the transfer pipette. So leave the short end and cut it about there. Push it through the stopper, and you want the thin end coming out the top. So the fat end, the thicker end will be on the inside, and the thinner end coming out the top. And you just push the tube over the thin end until it gets tight. So that's basically, now we have a stopper and we can collect gas and have it come out the tube on the other end. That is going to fit into our large glass test tube. So into the glass test tube, we put 5 grams of baking soda. Okay. And again, when you're putting something like this into a tube, bend it so you get a nice clean. That way it all goes in the tube. You don't get it all over the place. Then you can just tap the top of it like this. Then it's in the tube. No muss, no fuss. Okay. Then we take 10 mils of the white vinegar. And we get one of our polystyrene tubes, test tubes this time. So one of these. So it's not glass, it's plastic. We're going to put 10 mils of vinegar in there. So 10 mil graduated cylinder. And then you put this one, the small polystyrene test tube, inside the big one. But you don't add the vinegar. Don't pour it in. Just put it right in like this, so they're both facing up. Like, there you go. Now we take our little collection device that we have made and put that into the top. I think you can see what we're trying to do here. So now my tube has, the large tube has baking soda in it. The small tube inside of it has vinegar in it. And then on the top, I've got a stopper. And then basically there's only going to be one way for the gas to escape, and that's through this hose. So we should know what gas is going to be produced because we used this reaction already. So take our small glass test tube. It's getting a big workout this week. And we add the lime water. So the lime water comes in a small tube, just like the hydrogen chloride, the HCl. Make sure you don't mix them up. And then you put about half fill it in the small tube. Yeah, so for this one, you don't have to be super precise, but about halfway. And again, you do not want to get this on your skin because this is a strong base. All right, so about halfway filled. Okay. So I get my little cardboard tube holder, put it in there. I think you can see it right there. Take this other one out.
Professor?
Yep.
Is it okay if we continue the experiment tomorrow?
Yeah, I mean, I'm just going to finish up and then, I mean, I might as well finish up, right? I'm the only one doing it, so I'm going to finish it. All right, so I'm just going to turn this horizontal, and so the vinegar pours out of the smaller test tube and goes into the larger one, and that should start the reaction. There it goes. Oh yeah, we're getting some reaction. So you can see bubbles going into the there we go. The question is, am I seeing any reaction take place? Even though I'm getting gas, I'm getting gas bubbling into the lime water, but I'm not really seeing much of a reaction take place. It might take some time. I think I'm just going to let that sit for a while.
So aside from the bubbling in the lime water, there's supposed to be something else that happens?
Well, yeah, well, if you remember, there's calcium hydroxide in the lime water, and then CO2 is produced by the vinegar and baking soda reaction. And I'm supposed to get a precipitate of calcium carbonate in here, but it may take a little while for that to happen. Oh yeah, yeah. Yeah, so take this out and then let it sit for 5 minutes. So yeah, I think it takes a little time. Not all reactions are instantaneous. That's another important thing for us to learn tonight. Not all reactions take place immediately. So we've bubbled plenty of CO2 through here. So we let it sit undisturbed. So I think what happens is that this reaction slowly takes place and that we give it some time. So I'm going to just let that go for about 5 minutes or so. Get this out of the way. So the last one, pretty straightforward. Just pull yourself some steel wool. Get it really thin apart, but make sure it's spread out. You want to make sure as much of the metal is exposed to air as you can. Make like a thin mesh. And get the forceps. I've got the metal ones that I used last week. You might want like tongs or something like that. And then, see that? It actually caught fire. So I think, they want you to measure the mass? No. I can do that one more time because that's fun. Yeah, suggest you use a lot more, but I mean, you can use as much as you feel safe, burning your house down. It's just really cool to watch. Though do it over some water or like a cookie sheet or something, because it will release like little bits of burning metal that you don't. But yeah, it's a fun reaction. So you can see I still have quite a lot of this left. So you can do it multiple times. You can do a little bit more of it if you want. If you're a pyromaniac like I am. Yeah, you don't want to be holding on to it with your bare hands though. So definitely use some forceps. Would always freak out my high school students when Because they never think of anything burning other than wood or, you know, gasoline or something like that. When you show the metal can burn, it kind of freaks them out. All right, I'm just going to give this a little more, because I don't really see anything yet. Oh, wait a minute. Oh. Yeah, it's starting to get a tiny bit cloudy. It's kind of hard to see, but very slightly. So this might be one where it takes more time. You also might want to clean out the test tube, because we had like, you know, burned some things in there. So that may interfere a little bit, but I'm going to leave it for another little while. So, any questions before we go? Kind of hoped we get a little more participation since we actually did so many cool experiments, but there you go. So did anybody do the experiments tonight other than Rachel and Brandon and myself? Okay. Well, Ezekiel, you did them? Have you seen any precipitate from your from the lime water yet?
I didn't get to do that one because I couldn't get the tube inside of the hole. So then I'm just gonna do it another time.
If you have trouble, yeah, you can always take a little bit of Vaseline and put it on the outside of the tube, because if it's too tight. But yeah, I would suggest cutting it off.
Yeah.
Taking the thin end and just cutting it off about there, and then inserting this part through, because that'll go through easily. And then you just pull it through, and it should seal up nice and tight. Because yeah, the first time I tried it this afternoon, yeah, I just cut off both at the wide, you know, the widest part of the, and then tried putting that through, and that was really I
think that's what I did. Yeah,
that was a lot more hard to do. So I said, well, this is stupid. So I'm going to take advantage of the fact that this is narrow. So that worked much better.
I'll probably do that. Thank you.
Okay. So anybody else have any questions? So you know how to, so we're going to want pictures of your setups, you know, the observations, answer all the questions, and we want balanced reactions. So if anyone, you know, having trouble figuring out what the balanced reactions are for them, let me know, and I'll help you out with that. Okay. A lot of quiet people tonight. All right, I bid you good night, everyone.